Hello and welcome. In this video, we're going to take a look at the notes for Linear Dynamics AP Physics C. Remember to pause and rewind the video as needed. Let's begin. In this video, we're going to take a look at concepts involving Newton's laws for linear dynamics, as well as several examples, both involving numbers and variable only. In our first example, we have a hanging traffic light. Determine the force tension F sub t in the angled chords in terms of m, theta, and fundamental constants. Remember, when they say fundamental constants, they're referring to G. Well, the first thing we ought to do is we ought to draw the forces that are acting on this little section right here. We actually have two places to draw forces on. That little junction between three cables going up in this direction, and straight down. But then you also have the cable that is suspending the mass, and you have the weight of the mass, which is mg. We need to account for the tension in the cables. So this angle here becomes the same as this angle up here. This angle here becomes the same as this angle up here. And so since this tension actually points down from the knot that's right here and up from the mass, it's essentially going to cancel, and we're going to neglect that and consider it more or less an internal force. Let's focus on the external ones. Well, this particular component would be the adjacent side of F sub t. So this would be F sub t cosine of the angle, as with this side over here. This other side here would be the opposite side. That would be F sub t sine of the angle. And by looking at this, our horizontal forces are completely balanced, and quite honestly, it just gives an identity where the tension equals the tension, and that doesn't really help you solve anything. But vertically speaking, we can see that there are two forces going up and one force going down. So in the y direction, our forces are balanced. And we will use Newton's first law, which applied can help us equate forces going up to forces going down. Now, going up, you have force tension cosine of theta, but you have two of them. So I'm going to write 2 ft cosine theta equals the weight. Now, if we're solving this for tension, then I'm going to divide both sides by 2 and cosine of theta. The 2 cancels, the cosine cancels, and my tension force is equal to the weight divided by 2 times the cosine of the angle. Now, before you kind of finish off and box or circle your answers, you do a double check. We were told to write our answer in terms of m, theta, and g, which means those are the only things we're allowed to have in the answer. Well, we have m, theta, and g. So we are good to go as far as that being a final answer. Now, in the next example, we have two different angles. We have theta 1, theta 2, and thus we have two different force tensions, force tension 1 and force tension 2. Well, again, let's go ahead and force diagram this. We have weight equals mg going down. We have this angle is the same as theta 2 here. This angle is the same as theta 1 down here. Drawing our components would make this force tension 1 sine of theta 1. Over on the other side, it would be force tension 2 sine of theta 2. On the left side of M, we have force tension 1 cosine of theta 1. And on the right side of M, we have force tension 2 cosine of theta 2. So our forces break down like that. Okay, now what we're going to do is we're going to essentially put together our horizontal and vertical forces. So now the forces in the x direction would tell us that this force equals that one. So we have F T1 cosine theta 1 equals FT2 cosine of theta 2. Now you need to pick a variable to solve for, tension 1 or tension 2. It doesn't matter. I'm going to go ahead and pick tension 1, which means I'm going to divide by cosine of theta 1. And force tension 1 is equal to force tension 2 times this ratio of cosine of theta 2 over cosine of theta 1. This becomes the value of tension 1. Now we go to our second equation and look at our vertical forces. And in the y direction, you have a total of 3 forces. 2 forces go up and 1 goes down. So we have F T1 sine theta 1 plus F T2 sine theta 2 equals mg. Well, right about now is where we're going to take our value for tension 1 and we're going to substitute it right there in place of tension 1. I'm going to recopy everything else outside the parentheses and I'll substitute tension 1 inside the parentheses. So I've got times the sine of theta 1 plus F T2 sine of theta 2 equals mg. And the value of tension 1 that I'm plugging in there is FT2 cosine of theta 2 over cosine of theta 1. Now, I see sine of theta 1 divided by cosine of theta 1, so I could kind of rewrite this as FT2 cosine of theta 2 times the tangent of theta 1. Sine over cosine is tangent. Plus FT2 sine of theta 2 equals mg. Now, what I'm trying to do is solve for tension force 2. So I'm going to factor that out and divide away everything else. So this becomes FT2 times cosine theta 2 tangent theta 1 plus sine of theta 2 equals mg. So force tension 2 is equal to mg over cosine theta 2 tan theta 1 plus sine theta 2. Okay, there's our value for tension 2. And we just do a double check. We're only supposed to have m theta 1 and theta 2 and g, fundamental constants means g in our answers. We've got mg, theta 1, and theta 2. We're good. kind of a complicated looking answer, but it's written in the appropriate variable, so it works. Now, we're going to plug this in for ft2 in equation 1. Equation 1 was right here. So ft1 is going to be this value, this big, huge value for ft2, plugged it right in there, times what's left over, which is cosine theta 2 over cosine of theta 1. So we've got mg over cosine theta 2, tan theta 1, plus sine of theta 2. And at this point, I wouldn't bother simplifying it. Yeah, you could multiply mg times the cosine theta 2 on the top, and then you could distribute the cosine of theta 1 to everything on the bottom, but I don't really see the point. You don't get extra points for extra simplification as long as it's written in the appropriate variables, which are m, theta 1, and theta 2, then we are good. Determine the tension force Ft in the horizontal chord and Ft2 in the angled chord in terms of m theta and g. So you've got weight equals mg going down, you've got Ft1 going to the left, and you've got Ft2 going up at an angle. But we need components. This angle is the same as this angle, so this would be Ft2 cosine of my angle. The opposite side would be Ft2 sine of my angle. Now, if I look at my vertical forces tell me this force equals that, up equals down. Force up equals force down. So Ft2 sine theta equals the weight. And we could go ahead and divide away the sine part of it right there, and we have a value for Ft2. So Ft2 is equal to the weight over the sine of the angle. But then we're going to take that, because we're allowed to use m and theta and g, that's it. But we're going to take that value for F2 and we're going to use that in our horizontal forces. So our horizontal forces, we're balancing them as well, and that would be forces left, right, equal forces right. So forces left would be Ft1, that's the other force we're looking for, times Ft2 cosine of the angle. Well, that means Ft1 would be mg over the sine of theta, I'm substituting for Ft2, right there, times the cosine of the angle. Now, sine over cosine is tangent. Cosine over sine, like we have here, is cotangent. So you could leave it like this, that'd be fine, or you could write it as mg times the cotangent of theta. Either one would be fine. Well, Newton's first law tells us that objects moving at a constant velocity, which would either be at rest or constant speed, are going to keep doing so unless an unbalanced force accelerates the object. So basically, constant velocity results in forces being balanced. Constant acceleration results in forces being unbalanced. That, of course, is the nature of Newton's second law. An unbalanced force, or a net force, causes a mass to accelerate. And we typically wrote that as an equation, net force equals ma. And then we just rewrote net force as causing force minus opposing force equals ma. When we're talking about systems of masses, in other words, multiple masses connected by tension, we would just simply write this as causing force minus opposing force equals the sum of all your masses times A. We'll get to that shortly. Newton's third law tells you every force has an equal and opposite force. So the force exerted by one object is going to receive a force of equal magnitude back on it, but in the opposite direction. These are called action, reaction pairs, pair of forces. So object 1 exerts a force on object 2. Object 2 exerts an equal and opposite force back on object 1. Vertical motions and Atwood machine. A student stands on a scale in an elevator. The elevator can accelerate upward or downward. The mass of the student is 50, and the mass of the student elevator and the scale combined is 500. The elevator is accelerating upward at 2 meters per second squared. Draw force diagrams on the student and the elevator and determine the reading of the scale and the tension holding up the elevator. Well, the forces on the student specifically would be mg going down and normal force from the scale going up. The elevator, on the other hand, would be tension going up and big mg, the combined mass, going down. So if we focus on the student first, the student is accelerating because the elevator is accelerating. We would use Newton's second law, causing force minus opposing force equals ma. Now, if we're accelerating up, the causing force would be the normal force pushing on the student's feet, minus the opposing force of their weight equals ma. Add mg over to the side here, and normal force equals mg plus ma. We can factor out a common m, and it's m times g plus a, which would be 50 times 10 plus 2. And the normal force would be 50 times 12. Well, 5 times 12 is 60, so 50 times 12 would be 600 newtons. Now, that should make sense because the actual weight of the kid, the weight of the student, would be 500 newtons if the elevator was still. The weight and the normal force would balance each other. However, since the elevator is accelerating upwards, the floor and the platform of the scale is going to push on the student's feet with a greater force than their own weight, hence the 600 newtons instead of 500 newtons. Taking a look at the elevator. Accelerating as well, so causing force minus opposing force equals ma. This time the causing force is the tension minus the weight of the elevator and student and scale combined. So tension minus big mg equals big ma. Add mg over to the other side, and tension equals mg plus ma, or big M times g plus a. Big M would be 500 combined, times g is 10 plus a is 2, and we're looking at 12 times 500, or 6,000 newtons. There we go. Repeat this above, but this time for an acceleration going downward. So there's two ways we can accelerate downward. We could either be speeding up going down or slowing down going up. But either way, we can be accelerating downward. Now, if that's true, mg would be going down, normal force is up, tension is up, and big mg is going down. So the forces are the same. But this is how it's going to be different. For the student, we start with the same equation, causing force minus opposing force equals ma. But this time, the causing force is the weight. And the opposing force is normal force. Equals ma. We'll add normal force to the right, and we'll subtract ma to the left. And normal force is equal to mg minus ma. which is m times the quantity of g minus a, which would be 50 times 10 minus 2, or 50 times 8, or 400 newtons upward. I forgot to include that in my previous answers. The normal force and tension should both be up. Okay, looking at the elevator again. We have causing force minus opposing force equals MA, big MA. Causing force is tension minus big mg equals big MA. Scratch that. We're accelerating downward, so big mg minus tension. Big mg is now the causing force. Tension is now the opposing force. I'm going to add tension to the right, subtract MA to the left, and tension equals big mg minus big MA. Factor out a big M, G minus A, and it's 500 times 10 minus 2, and 500 times 8 would be 4,000 newtons pointing up. In the next example, we have what is known as an Atwood machine. Atwood machines consist of two unequal masses, big M and little m, where big M is greater than little m, attached by a light string over a massless, frictionless pulley. Determine the acceleration of the masses once they are released from rest. Well, when they're released from rest, big M wants the system to accelerate in its direction, and little m would thereby accelerate up. Since they're connected by a string, the two accelerations are the same. Therefore, we can work on the acceleration of a system overall. And we're going to be using Newton's second law to describe that. First, let's figure out the forces. Technically, we have weight equals little mg, and we have another weight equals big mg. So we kind of have a weight 1 and a weight 2. We also have a tension going up this way and a tension going that way. Now, when we work on acceleration, to find acceleration, we're going to use Newton's second law for the system of masses. And ignore tension. Now, we'll use tension, we'll use individual masses when we're trying to find tension. But now we're going to ignore tension because tension is essentially pointing at each other from each mass. Essentially, the tension will cancel out algebraically. So we're going to ignore it, consider it an internal force, and we'll focus on external ones. So causing force minus opposing force equals sigma MA. Now, what is this going to be? Well, the causing force causes the whole system to accelerate. So the causing force would be big mg. And what's opposing the whole system's acceleration? Well, in this case, it would be little mg. So big mg is the causing force minus little mg is the opposing force, and that's going to be equal to the sum of the masses, which is big M plus little m times A. Solve for A, and I'm going to factor out a g there, so it's big M minus little m over big M plus little m times the factored out g. There's our acceleration. Now, if we want to figure out the tension, we can use either mass, okay? If we use little m, then focusing on little m's tension, we have causing force minus opposing force equals little ma. That would now be tension minus little mg equals little ma. Add mg to the other side, and tension equals little mg plus little m times, then we're going to plug all that in for A. big M minus little m over big M plus little m times G. Again, there's no need to simplify. You don't get any extra points for doing that. As long as it's substituted correctly and you're including the variables that we were introduced to and only using those variables. Okay. Now let's determine the acceleration for the system that is shown here. Well, since we have the same situation as we have up there, I'm going to kind of jump to the equation that we derived, which was the difference in the masses over the sum of the masses times G. So the difference in the masses would be 9 minus 6 over 9 plus 6 times 10. That would be 3 times 10 over 15. Acceleration would be 30 over 15, or 2 meters per second squared. Now, how do we find tension 2, which is connecting both of those strings? First, find the acceleration of the system, then we can choose this block here, which has a little weight, mg, and ft2 going up. Now, you might notice that 7 kilograms and 2 kilograms is pointing down as a big mg, and 6 kilograms, just like you saw here, was pointing down as a little mg. So numerically, this is working out exactly the same way that we had up here, which means we're going to end up with the same result for acceleration. The difference in the mass is the big M coming down on the right side would be 7 plus 2. 7 plus 2 minus 6 over 7 plus 2 plus 6, and then times 10. Okay, that would be, of course, 9 minus 6, 9 plus 6 times 10, or 2 meters per second squared, just like we had before. So we need that information from before. Now I'm going to choose, since I know that this first mass is accelerating upward, I can go ahead and choose that mass. So we know that causing force minus opposing force equals little ma, which would be tension going up, minus little mg going down equals little ma. Adding mg to the right, we have tension equals little mg plus ma, which would be m times the quantity g plus a, which would be little m is 6 times the quantity of 10 plus 2, and we'd get 72 newtons. And I just made a big oops because we didn't want to find 72 newtons. That's the tension across this one right here. But oops, I didn't pay attention to the question, and we were looking for that tension right there. So I'm going to back this up just a brief bit, and instead of using this mass here, I'm going to use this mass right here to find that missing tension too. So the causing force would be the mg of the 2 kilogram mass going down minus ft2 equals ma. Add this to the right, subtract that to the left, and ft2 is equal to mg minus ma, which is m times the quantity of g minus a, or 2 kilogram mass times 10 minus 2 again. And 2 times 8 would be 16 newtons. So the other tension was 72 newtons, but oops, we weren't asked to find that. We're looking for the tension in between the blocks, which would be 16 newtons. Well, the purpose of friction is to resist or even prevent, in some cases, the motion of an object. Static friction occurs when two objects are not sliding against each other. Kinetic friction occurs when two objects are sliding against each other. And let's go ahead and take a look at this example here. We have three masses pulled by a force of 30 newtons, and we want to determine the acceleration of the block and the two tensions in between. Now remember, when we want to find the acceleration, find acceleration of the whole system first, which means we ignore tensions to begin with. Now let's talk about what the free body diagram is for the whole thing, because we'll eventually have to find tensions. We have M1G and normal force 1, and we have force tension 1 going to the right. Mass 2 has force tension 1 going to the left, normal force 2, and M2G. But it also has force tension 2 going to the right. M3 has force tension 2 going to the left, has applied force F going to the right, has normal force 3 going up, and M3G, the weight, going down. So to find acceleration, we're going to use Newton's second law applied to the entire system. Causing force minus opposing force equals sigma MA. The causing force would be F. Any opposing force would be like friction opposing the movement of any of those blocks. And since it is frictionless, we do not have an opposing force for this example. So the applied force F is equal to the sum of all the masses. That would be M1 plus M2 plus M3 times A. Let's go ahead and find a value for A. And it's going to be the force divided by the sum of the masses. And we have 30 newtons divided by 1 kilogram plus 2 kilograms plus 3 kilograms. And 30 newtons over 6 means the acceleration is about 5 meters per second squared. So there's the first part. Now, in order to find the tensions, what we have to do is we have to choose two masses. Well, to find tension 2, I'm going to use mass 3 because I can use the force going forward and tension 2 going backward. To find tension 1, I'm going to use mass 1 because I can really just focus on tension 1 pulling it forward. So let's first find tension 1. We have causing force minus opposing force equals M1A. That would be force tension 1 minus nothing, because there is no opposing force going backward, equals M1A. Then force tension 1 would be equal to M1A. So M1 is 1 kilogram times A, which was 5 meters per second squared. And that tells you that that's going to be 5 newtons of tension pulling on that last block. Now, to find the tension 2, I'm going to use the third block. The third block, when we go causing force minus opposing force, is going to be equal to M3 times A, and that's going to be the applied force minus force tension 2 equals M3A. I'm going to add force tension 2 to the right, subtract M3A to the left, and force tension 2 is equal to the applied force minus M3A, which would be 30 minus 3 times 5, or 30 minus 15. Force tension 2 would be 50 newtons. I think that should make sense. It should make sense that tension 1 is going to be less because it's only pulling one block. Tension 2, on the other hand, is pulling 2 blocks. Pulling more mass is going to pull the rope tighter. Now we're going to redo the exact same problem, but this time we have friction on the ground. So let's redo the diagram. We've got normal force 1. We've got M1G. You've got force tension 1 to the right, and you've got friction 1 equals mu N1 to the left. You've got force tension 1 going to the left of M2. You've got normal force 2. By the way, normal force 1 is balancing weight 1, so it's also M1G. This is also M2G. Okay, we also have friction 2 is equal to mu N2 going to the left. On the third mass, we've got normal force 3, which is balancing M3G going down. You also have friction 3 is equal to mu N3. Okay, do keep in mind friction 1 would now be equal to mu M1G. Friction 2 would be equal to mu M2G. And friction 3 would be equal to mu M3G, because you're replacing normal force 3 with the weights. Okay, to find the acceleration, we're going to do exactly the same thing we did before. Newton's second law. Causing force minus opposing force equals sigma ma, total mass accelerating. Your causing force is still F. But this time you have 1, 2, 3 opposing forces. So you're going to subtract all of them. So minus F1, minus F2, minus F3. We have 3 opposing forces. Equals the sum of your masses times acceleration. Divide out the sum of your masses, and we've got mu times M1G minus mu times M2G minus mu times M3G, all over the sum of the masses, M1 plus M2 plus M3. Okay, let's sort this out. F was 30 from before, it's still 30 now. Mu, given in the problem, is 0.2. So we're going to go 0.2 times weight 1. Now, weight 1 is 1 kilogram. 1 times 10 is 10 newtons. Weight 2 is 20 newtons. Weight 3 is 30 newtons. So we're going to go 0.2 times 10 plus, or sorry, not plus, minus 0.2 times 20 minus 0.2 times 30. All of that is over the sum of the masses, 1 plus 2 plus 3 kilograms. So we're going 30 minus 2 minus 4 minus 6 over 6. And that would be 30 minus 12 over 6, which comes out to 18 over 6. And the acceleration this time is 3 meters per second squared. So the acceleration when we were frictionless was 5. It should make sense that the acceleration is less because we have an opposing force now. To do and find the tensions, I'm going to do it exactly the same way. I'm going to use M1 to find tension 1, and I'm going to use M3 to find tension 2. So to find force tension 1, I'm going to use Newton's second law, causing force minus opposing force equals M1A. That would be force tension 1 minus friction 1 equals M1A. Add friction 1 to the other side, substitute what it is, and we get force tension 1 equals mu M1G. Plus M1A. You can factor out an M1 if you want to. And it's mu G plus A. And force tension 1 would be 1 kilogram times mu G, which is 0.2 times 10, plus 3. And 0.2 times 10 is 2, plus 3 is 5 newtons. Finding force tension 2 again, I'm going to use the third mass. Again, causing force minus opposing force will equal M3A this time. And we're going to have F as my causing force minus 2 opposing forces. You have F2, FT2 going to the left, but you also have friction 3 going to the left. So FT2 minus friction equals M3A. Well, to solve this one, I'm going to be adding FT2 to the right and subtracting M3A to the left. So FT2 is going to be equal to F minus friction minus M3A. And we'll plug into that. And this is friction 3, by the way. So we have FT2 is equal to 30 minus mu M3G, which would be 0.2 times 30 minus 3 times 3. And we've got 30 minus 6 minus 9. 30 minus 15 essentially is 15. So something to note, when you're pulling a series of masses all connected by tension, while the acceleration might be different because the net force is different, the individual tensions are exactly the same. Not a coincidence. A block of mass is pulled by a 50 Newton force at 37 degrees to the horizontal. Determine the normal force and the acceleration if the surface is frictionless. Well, we've got normal force up, weight equals mg going down, no friction to the left, and you've got the applied force going up and to the right. We need components of F. Since this is my angle, the adjacent component would be F cosine of theta. The opposite side, would be F sine of theta. Starting with our vertical forces, normal force and F sine both go up. So we're looking at forces up equal forces down. So normal force plus F sine of theta equal the one force going down, which would be the weight. Subtract F sine over to that side, and normal force equals mg minus F times the sine of theta. Plug in our values. M is 5 times g is 10 minus F is 50 sine of 37 degrees. Okay, so normal force would be 5 times 10 is 50. 50 sine of 37 would be about 30, and that would come up to about 20 newtons upwards. Now, to find the acceleration, we have to find the forces in the x direction because they're unbalanced. We're going to use Newton's second law, in which case causing force minus opposing force equals ma. The causing force is going to be F cosine, and there is no opposing force. So F cosine of theta equals little ma. Divide away the mass, and A is equal to F cosine divided by the mass, which would be 50 cosine of 37 over 5. Which comes out to about 40 over 5, which is 8 meters per second. Let's repeat the exact same problem. This time, let's include friction. Normal force up. Weight equals mg going down. F cosine goes to the right. F sine is the vertical component going up. And friction is fun goes to the left. Well, your vertical forces are exactly the same. Normal force plus F sine. Balance your weight. Subtract F sine to the other side. Normal force equals mg minus F sine. So since everything's the same, I'm just going to kind of plug in and use what we had before, which was 20 newtons going upward. So, well, that didn't really change. Okay, so, and that's actually not an answer we're trying to find, but we need it though. We need it to solve the problem. Now, to find the acceleration of this block, we now need to use the forces in the x direction, Newton's second law, which tells us causing force minus opposing force equals ma. The causing force is going to be F cosine theta because we are accelerating to the right. We do have an opposing force of friction this time going to the left, and we're going to set that equal to ma. Solving for acceleration, we're going to divide by the mass again. And so we've got F cosine of theta minus friction, which is mu times normal force, over the mass. So plugging in, we have 50 cosine 37 minus mu, which was 0.5. 0.5 times n was 20, so half of 20, over the mass, which was still 5. That didn't change. So 50 cosine 30, if you remember, was 40 minus half of 20, which is 10, over 5. And 30 over 5 is 6 meters per second squared. So as expected, when acceleration is going to reduce when the net force goes down, the net force went down because you have opposing friction, right? Reducing the net force. Let's take a look at another system where we have a horizontal mass on a frictionless surface and a vertical mass hanging over the end of a pulley. Well, the free body diagram of this would look like capital mg going down, normal force going up, tension going to the right. Now, if this was a rough surface, you would have friction going to the left, but there is no friction in this problem. On little m, you have tension going up and little mg going down. To find A, you're going to use Newton's second law for the system, just like we have been, which means causing force minus opposing force equals sigma ma. The problem is we got to figure out what the causing force is. Well, what causes the whole system to be unbalanced? Well, block M accelerates down and block big M accelerates to the right. So what accelerates the whole system? mg. So that would be our causing force. An opposing force would be horizontal on the table going to the left. Well, since there's no friction, there is none. So the causing force is going to be little mg equals the sum of the masses, big M plus little m, times A. Divide the sum of the masses, and we have little mg over big M plus little m. Little m is 8 times g is 10 over the sum of the masses, which would be 8 plus 12. And we get 80 divided by 20, which is 4 meters per second squared. Now, to find tension, you have to basically choose a mass. So I'll go ahead and use big M. Big M is accelerating to the right. So if we use our Newton's second law, causing force minus opposing force equals big MA, we have no opposing force. And this would be tension equals big MA. Or tension equals 12, which is big M, times A, which is going to result in 48 newtons of tension. Now, just to show the comparison, what if we had chosen little m, this mass right here? Well, in this case, if we used little m, we would have causing force of mg minus tension this time is the opposing force equals little ma. Add tension, subtract MA, and tension equals mg minus MA. Or little m times g minus A, which would be 8 times 10 minus 4. And 10 minus 4 is 6, times 8 is 48 newtons. So you'll see you'll get the same result no matter which mass you choose. But when you have to find tension, you have to choose one of the two. Let's repeat the exact same problem with a coefficient of friction of 0.5. So we know we have little mg going up. We've got tension going, or excuse me, down, tension going up. Tension pulls this one to the right to accelerate to the right. Little m accelerates down. We have big mg of weight going down. We have normal force going up, which is balancing big mg. So normal force is mg. And you've got friction is fun going to the left. Now, since normal force is big mg, that means friction is going to be mu times big mg. We'll need that substitution for later. Well, let's do this. Causing force minus opposing force equals the sum of the masses times acceleration. Well, the causing force is still going to be little mg. But this time there is something opposing the whole system, and that's friction, which is mu times big mg. And that's going to be equal to the sum of the masses, big M plus little m times A. Go ahead and solve for A. And we have little mg, which would be 8 times 10 minus a half of 12 times 10. All divided by the sum of the masses, which is 12 plus 8. So we've got 80 plus half of 120, which would be 60, over 20. Oh, excuse me, not adding, subtracting. And so we get, what do we get here? 20 over 20, which would be 1 meter per second squared. So as expected with friction, we reduce the acceleration from 4. It reduces down from 4 to 1. But what we saw in the previous situation, that the well, let's go ahead and find the tension. Again, you can choose either mass. Okay, so if I'm going to choose, let's say I choose little m this time. That means causing force minus opposing force equals little ma. The causing force is mg, the weight, minus tension going up equals ma. Add tension to the right, subtract little ma to the left, and tension equals mg minus ma, which would be m times g minus a. And that would be 8 times 10 minus 1. 10 minus 1 would be 9, and that times 8 would be 72 newtons. Okay, now I'm not going to do it in this particular one, but had you chosen big M to accelerate to the right, you would have also gotten 72 newtons of tension on that one as well. Now, with inclined planes, one thing that you want to set up all the time and make it consistent is you're going to have M going straight down, mg rather, going straight down. You're going to have normal force going perpendicular out of the plane. And what we're going to do is we're going to take our normal y and x axes and we're just going to shift the direction so that the y-axis goes perpendicular to the plane and the x-axis goes parallel to the plane. We're just shifting our reference frame, which means we're going to need components for the weight. You're going to go down, stop, and then you're going to go down the plane. You're going to have one component that is perpendicular to the plane, and you'll have a second component that is parallel to the plane. Turns out that the angle of incline is the same as the top angle up here, which makes the vertical component mg times the cosine of the angle, since this is the adjacent side. Since this is the opposite side, that makes this mg times the sine of the angle. So these are the things that happen for every inclined plane problem. Normal force goes perpendicular out of the plane. It balances mg cosine going into the plane, and mg sine always goes parallel down the plane. Now, what happens in the problem is completely unique to the problem, meaning whether there's friction, which way friction points, is there any applied force or tension in the problem. Those are case-by-case basis. However, what we just drew here is true for any inclined plane problem. First, let's find the normal force. So normal force is a vertical force. We're going to balance our forces. Up equals down. Do keep in mind that up means in the positive y direction. Down means in the negative y direction. So normal force does not equal weight. It equals weight cosine of the angle. So normal force would equal 10 kilograms times 10 times the cosine of 37 degrees. And that would be 100 cosine 37, or about 80 newtons. I'm just rounding it up a little bit. Okay, to find the acceleration down the block, I'm going to use the forces in the x direction, which means I'm going to use Newton's second law. Causing force minus opposing force equals ma. Now, the causing force goes in the same direction as acceleration, which is downhill. The only force going downhill is mg sine. The opposing force would naturally have to go up the hill. Since there is no friction or any other opposing force, we don't have one in this example. And that equals ma. Notice the masses cancel, and a is equal to g sine theta, which is going to be 10 times the sine of 37 degrees. And 10 sine 37 would give us an acceleration of about 6 meters per second squared. Let's repeat the exact same problem, but with the friction. Remember, we start with mg going down and normal force going perpendicular out. We have components of weight. Mg cosine is opposite the normal force, and mg sine goes down the plane. This time we have friction is fun going up the plane. So in the y direction, normal force still balances mg cosine. So that didn't change. That's going to be 10 times 10 times the cosine of 37 degrees, which is still going to be 80 newtons. Okay, now we want to determine the frictional force and the acceleration. So the frictional force is going to be mu times normal force, or 0.5 times the 80 newtons, which would be 40 newtons. The acceleration requires the friction. So to find the acceleration, we're going to use Newton's second law. Causing force minus opposing force equals ma. The causing force still points downhill, which would be mg sine minus friction. Friction is our opposing force. That equals ma. Divide the m, and it's going to be mg sine, which would be 100 sine 37 minus 40 for friction, divided by our mass, which was 10 kilograms. And when we go 100 sine 37, so let's see, 37 sine times 100, we're at about 60. So 60 minus 40 over 10, which would be 20 over 10, which would be 2. Again, that should make sense. If the net force is getting smaller, then the overall acceleration should have gotten smaller. Well, now we've got a system of masses connected by tension, but one is on an inclined plane. In this first situation, it's a frictionless incline. So you've got big mg going down, tension going up, normal force going out, mg going straight down, mg cosine balancing the normal force, and mg sine pointing downhill. Now, since m is significantly bigger than little m on the incline, the system's going to accelerate in the direction of the falling mass. That means big M accelerates down and little m accelerates up the plane. Find the acceleration of the system first. To do that, we're going to take the causing force, which is mg, minus the opposing force, which would point downhill. That would be mg sine. So causing force minus opposing force equals sigma ma. That would be big mg minus little mg sine theta equals the sum of the masses big M plus little m times A. Solve for A by dividing by the sum of the masses, and we can plug in. So big mg minus little mg sine theta over big M plus little m. So big M was 30 times 10 minus a little m, remember little m was 10 already, times 10 for g times the sine of 37 all over 30 plus 10. The acceleration is going to be 300 minus 100 sine 37 over 40. So we have 300 minus, that would be 60 over 40. 300 minus 60 would be 240. And 240 over 40 would be 6 meters per second squared. To find tension, again, you just need to choose a mass, either the falling mass or the one rising up the incline. I'm going to use big M to find tension. So causing force minus opposing force equals big MA. The causing force would be the big mg going down minus the tension pulling up on it equals big MA. Add the tension to the right, subtract MA to the left, and tension equals big mg minus big MA, or big M minus the times the quantity of big G minus A. That would be 30 times 10 minus 6. 10 minus 6 is 4, times 30 would be 120 newtons. And you would find if you used little m, you'd get 120 newtons of tension pulling that if you had calculated that one too. Let's repeat the exact same question, but with friction. We have big mg going down, tension going up the plane, normal force going out of the plane, mg going straight down, mg cosine balances the normal force, mg sine goes down the plane, and friction also goes down the plane. But now its friction is normal force, and normal force, this would be mu, mg cosine, since those two are balanced. I'm just kind of making that substitution right now. So to find acceleration, you're going to use the whole system again. So causing force minus opposing force equals sigma ma. The causing force is still big mg, but this time you have two opposing forces right here. So minus friction minus mg sine equals the sum of the masses, big M plus little m times A. Well, we have big mg minus friction, we already saw, turns into mu mg cosine minus mg sine equals the sum of the masses times A. Let's divide by the sum of the masses and plug in. So we still have 30 times 10 minus 0.5 times 10 times 10 times cosine of 37 minus 10 times 10 times the sine of 37 all over the sum of the masses, which would be 30 plus 10. So acceleration is going to be 300 minus 60 minus 40 all over 40. 30 minus 60 minus 40 is 200. 200 over 40 would be 5. Again, as we expect, as the net force goes down due to the resistance of friction, acceleration is also going down from 6 to 5. Finding the tension, I'm still going to choose, I'm going to use big M to find tension. So big M, we're going to use causing force minus opposing force equals big MA. The causing force of that particular acceleration would be big mg minus the tension that opposes it equals big MA. Let's add tension to the right, subtract MA to the left. And tension equals big mg minus big MA, or big M times the quantity of g minus A. So this would be 30 times 10 minus 5, 30 times 5, or 150 newtons. Does make sense that the tension has to go up in these situations involving friction, not in a straight line like the first example, but these last two examples we've done right here where the system is not in a straight line, and there is an element of friction, you would expect more pull on the rope because you have more resistance. Same thing here. We have more pull on the rope, so we have more resistance, more pull on the rope. It goes up from 120 to 150. Not a surprising result. In this next section, we're going to talk about resistive forces. Now let's consider a ball of mass m drop from rest. As it falls through the air experiences a force of air resistance given by F of little r equals K times V. Something to note about how air resistance works. At time equals 0, an object would just experience mg and no air resistance whatsoever because air resistance is proportional to speed and you're dropping from rest. Now, at time equals, let's say, 1 second, well, you've got the same weight, but this time you have a little more air resistance. Not quite the same. What does this mean? Your acceleration was g. Now your acceleration is going to be less than g. Your acceleration is decreasing because you have a net force now. The net force has gotten smaller, therefore g. The acceleration has gotten smaller. And you're going to reach a time when you eventually reach what's called terminal velocity. And when terminal velocity is reached, that is when the air resistance going up balances that same weight going down. And terminal velocity is constant velocity the rest of the way. And acceleration has basically reduced to 0. Well, let's draw the forces on the ball. So at some time afterwards, we have mg going down, and you have the resistance force equals kv going up. Write an expression for the terminal velocity. Well, remember, what did we say about terminal velocity? That's when acceleration goes to zero, right? So we would have essentially our forces would be balanced. K times Vt, the Vt is going to stand for terminal velocity, going up, forces going up, equal forces going down, which would be mg. Divided by k, and our terminal velocity would be the weight divided by k. What k represents is it represents a coefficient of what's called a drag coefficient, which could be related to the viscosity of the fluid you're passing through, the aerodynamic nature, the geometry of the actual object that's passing through, meaning, how much surface area is interacting with the fluid that is passing through. So K kind of represents a lot of things. And so it's just referred to as the drag coefficient, but it really encompasses a lot. Now, when it asks you to write a differential equation, that means write an equation with a derivative. Okay, well, how do we do that? Well, remember, acceleration is the derivative of velocity with respect to time. So what we can do is we can write a normal Newton's second law formula, causing force minus opposing force equals ma. And for a dropped ball at any time t before you reach terminal velocity, you'd have mg going down, causing it, minus kv going up, resisting it, equals ma. All we do to turn this into a differential equation is substitute dv dt for a, and that's it. We get mg minus kv equals m dv dt. Now, at a later time, I'll show you the integral calculus that's needed. There's about a total of 10 steps. There's about 3 calculus steps and about 6 more logarithmic algebra steps that would help you solve for velocity as a function of time. We're going to save that for a later lesson when you've had a chance to learn U substitution. For now, this will suffice in just writing the differential equation, but not actually solving it. Okay, so let's sketch the graphs of acceleration, velocity, and position for the time of the ball. Now I'm going to mark a time t on each of the graphs, and time t is when we have reached terminal velocity. Okay, so you're going to start the graph at g. At time equals 0, you're falling with g. And that's going to decrease to 0 as time goes on. Which means if that's happening, then the velocity is increasing, but it's going to level off at time t because this value right here is the terminal velocity, the constant velocity that you fall the rest of the way with. And that happens at some time t. And at that sometime t, you're going to accelerate, so you should expect a curve, but then you fall for constant velocity the rest of the way, so we should expect a straight line for the rest of the path. Now, the next section involves what's called uniform circular motion and banking of a curve. Well, the quantity, this letter here is the Greek letter omega, and it stands for 2 things. For rotation terms, it stands for something called the angular velocity, and we'll see more of that next semester. But it also stands for something called the angular frequency, which relates to periodic motion, and rotation represents something that's moving in a circle, represents periodic motion. So we're going to kind of go with angular frequency on this one. And it's related to the equation linear velocity is equal to r times omega. So it's related through the radius. Radius times the angular velocity equals the linear velocity. Now, it's also related to frequency and period. Frequency is how often something moves in a cycle, how many cycles you have every second, and period is the time it takes to complete one cycle. So we could relate this as W equals 2 pi times the frequency. 2 pi meaning relating to one complete full cycle, because one circle or 360 degrees is 2 pi radians. Or it's 2 pi divided by the period. Why is that? Because frequency is the inverse of the period. They're inverse concepts. That's why this works. Let's take a look at this next example. We have a puck of mass 4 kilograms is attached to a string which passes through a hole in a table and is connected to a hanging mass of positive 20 kilograms. The puck moves around in a circle of radius 2 meters at speed v. The table is completely frictionless. Determine speed v the puck must move in order to keep the mass at rest. Well, if the hanging mass is at rest, then big mg balances tension going up. Now that same tension is also pulling to the middle of the circle and causing M to go in a circle, which means tension is not only balancing big G, tension balances mg, and tension is a centripetal force. Centripetal forces cause circular curvature. Okay, now if we look at that puck from a side view, here's the table, here's M. You've got the normal force going up, you've got mg going down, you've got tension going inward to the middle of the circle. So focusing on big M, forces going up, equal forces going down, therefore tension going up equals big mg. If I focus on little m, we are accelerating centripetally. Now, centripetal acceleration, A sub c, is equal to v squared over r. So centripetal force, instead of ma, is going to be written as mv squared over r. It's just a small adjustment we'll make. We're still going to use Newton's second law, and it's still causing force minus opposing force equals ma. But now A is going to be written as v squared over r. Causing forces point into the circle, opposing forces oppose the curvature and would point out of the circle. Since there is no force pointing out of the circle in this one, there is no opposing force. The causing force is tension, and so we would say tension equals mv squared over r. But wait a minute, what was tension? It was mg. So we could replace this and say big mg equals little m v squared over r. Now to solve for v, we need to multiply by r, divide by little m, and then square root. So v would be the square root of little r, big mg, over little m. So r, the radius, was 2 meters, times big M, which was 20, times g, which is 10, divided by little m, which was 4. Well, 4 goes into 20 5 times. 5 times 10 is 50, times 2 is 100, right? Square root of that is, of course, 10. In this next example, we have a roller coaster car of 100 kilogram mass encounters a vertical loop of 40 meters, and it maintains a fairly constant speed of 40 everywhere around the loop. We want to find the normal force at the bottom and at the top of the loop. First, start with the diagram. At the bottom, you have mg going down, but it's not just going down, it's going out of the circle. And you have normal force not just going up, but going in towards the center of the circle. At the top of the loop, you have normal force pressing down on the roller coaster, but down is really towards the center of the circle. And the weight, which always goes down, is pointing towards the center of the circle. Let's focus on the bottom of the circle first. Causing force minus opposing force equals mv squared over r, Anytime we move it in a circle, we are accelerating centripetally. Okay, causing forces point into the circle. So this would be normal force. Opposing forces point out of the circle. That would be weight. So normal force minus weight equals mv squared over r. Go ahead and add the weight over here. And normal force equals mv squared over r plus mg. Now let's plug in the numbers. Normal force at the bottom would be little m, so we have 100 times a v, which is 40, and we're going to square that, over the radius, which was 40. Okay, now this is pretty easy because one of these 40s will cancel with one of those factors of 40s, and what's left is 4,000. Okay, but we have to add this to 100 times 10. So 4,000 plus 1,000, right, is 5,000 newtons at the bottom. Now at the top, it's going to be kind of the same thing, but here's the difference. You have two forces that point into the circle, which means you're going to have two causing forces. But you're going to have no opposing forces because you have nothing pointing out of the circle. Nothing points, no force goes up. All the forces go into the center. So this would become normal force plus mg equals mv squared over r. Subtracting the mg, normal force is equal to mv squared over r minus mg, which would be 100 times 40 squared over 40 minus 100 times 10. Again, this now would be 4,000 minus 1,000, or 3,000 newtons. So the normal weight is 1,000. If the roller coaster is at rest, the weight of 1,000, that's the normal force. That's what it experiences. But every time we go through a loop, we feel just a bit heavier. It turns out if we're going constant speed through this loop, we're going to feel the heaviest at the bottom, 5,000 newtons, 5 times the weight. This would be called, we would be experiencing 5 Gs, or 5 times our weight, 5 times gravity. Here we would be experiencing at the top 3 Gs. What is the minimum speed required for the car to complete the loop without falling off the track? Well, anytime we see that phrase minimum speed, that basically means the track is having very little contact and is not really forcing the car in a circle. Therefore, normal force reduces to 0. So if I go to the top and I use the equation normal force plus mg equals mv squared over r, but set normal force to 0, you're literally left with mg equals mv squared over r. In other words, it's just the weight that causes the curvature at a minimum speed. Masses cancel, and this would be v min multiplied by r square root, and v min is equal to the square root of gr, or the square root of 10 times the 40 meter radius. And if we, the square root of 400 is about 20 meters per second. In this next example, we have this ball, a mass of 3 kilograms moves with 20 meters per second in a horizontal circle of radius 30 meters on a string that makes angle theta with the horizontal. Determine the theta, angle, and the tension. This is an example of what is known as a conical pendulum. We have mg going down. You have tension going up. We need components of tension. This angle goes this way, equal to that angle. This would be tension times the sine of theta, making this tension times the cosine of theta. Now, We can start in pretty much any direction you want. I typically like to start in the y direction. And forces up will equal forces down on this one because we're accelerating horizontally. We're moving in a horizontal circle. Circle means accelerating centripetally. But the ball is not moving up or down, so it's not accelerating up or down. That means the tension sine theta that's going up equals mg, which is going down. We'll divide by sine theta. And tension equals the 3 kilogram mass times 10 divided by the sine of the angle. Now, I don't know what the sine of the angle is, so I'm going to leave that one blank, and we're going to come back and finish this problem. Okay? So right now, I don't quite know what is there yet. Okay? But we're going to come back to it. So in the x direction, you are accelerating centripetally, which means we have causing force minus opposing force equals mv squared over r. Very specific kind of acceleration. Causing forces point into the circle, opposing forces point out of the circle. There are no forces pointing out of the circle, so there are no opposing forces. Tension cosine theta is our causing force. That equals mv squared over r. Well, the value of tension, if you remember, was mg over sine. So we're going to substitute that right there. And we get mg over sine times cosine equals mv squared over r. And actually, this is one way to continue. Okay, we would basically have mg times the cotangent of theta, right? And we would take the inverse cotangent to do that, which is a little bit difficult because there is really no inverse cotangent on your calculator. You'd have to do a reciprocal identity of 1 over tangent, and this is just kind of leading to more work, essentially. So there's another way to solve this, and this is going to be a very convenient way when you have forces at angles and tension at angles and normal force at angles, and we're going to use this strategy a few times in the next few problems. And instead of substituting one equation into the other, another strategy you can do is to divide the equations one by the other. Here's how that would work. I can take the first equation, which is t sine theta equals mg, and divide that whole equation by the second equation, which was t cosine theta equals mv squared over r. Why is this helpful? Because by dividing, you can essentially cancel variables. Sine over cosine is tangent. So tangent of theta equals g over v squared over r is g times r over v squared. Okay, now you're solving for theta. We need to find theta first so we can plug theta back in here and get tension. So theta would be the arctangent of gr over v squared. So 10 times the radius, which was 30, over v squared, which is going to be 20 squared. So 3 times 10 is 300. 20 squared is 400. And so we're taking the arctangent of 0.75, which is 3/4. And that's approximately 37 degrees. Take that same 37, apply it up here, and we're going 30 divided by sine of 37, and 30 over sine of 37 is approximately 50 newtons of tension. The next example is called a banked curve problem. A banked curve is a way for a car to essentially make a turn around a curve without friction in the tires causing it to curve. In other words, the road itself pushes against the car, and a fraction or a component of the normal force is what causes the circular curvature. Let's take a look. We have a massive car, 1,000 kilograms, drives on a banked roadway with a radius of curvature 120 meters and a banking angle of 37 degrees. If the car moves at a constant speed v around the track is frictionless, then there is an exact speed the car must travel in order to successfully navigate the curve without falling off the road. Let's determine the speed. Well, here's what we're going to do. It looks similar to an inclined plane, but it's not going to be treated the same way. I'll show you why. We do start off by drawing the same variables, though. Normal force out of the plane, weight straight down. This time we are not going to make components of weight like we did before. Instead, we're going to make components of the normal force. Okay, here's why. The acceleration is going towards the center of the circle. It's centripetal acceleration. Well, you don't want a vector going downhill. That's not going to help you. You want a vector that's going straight to the right, which is inward towards the center of the circle. That would be this component of the normal force right there. Now, if you do a little bit of work with similar triangles, this angle is the same as this angle. And because those two angles are vertical, that is the same angle as the angle of incline. That makes this n cosine, and it makes the top component n sine. Again, you're going to come up with two equations, one in the y, one in the x direction. I like to always start with the y direction. It usually has less variables to work with, but sometimes the y is needed for the x. So in the y direction, we're balancing our forces, and normal force cosine theta going straight up equals mg going straight down. In the x direction, you're accelerating centripetally. So causing force minus opposing force equals mv squared over r. There are no outward forces, so there are no opposing forces. And the causing force would be n sine theta equals mv squared over r. I'm going to call this equation 1. I'm going to call this equation 2. Let's use the strategy we did before, and let's divide these equations. I tend to like to make sure that cosine is on the bottom because sine over cosine is tangent. So I'm going to put this equation here. I'm going to put equation 2, write that first. And I'm going to divide equation 2 completely by equation 1. Just like that. You'll see normal force cancels again, mass cancels again, and we end up with tangent of theta equals v squared over rg. We're looking for v min. We're looking for that speed. So we have to multiply by gr or rg and then square root. So v is going to be the square root of r times g times the tangent of the angle. Well, the road is 120 meters to the center times g is 10 times the tangent of 37 degrees. So 1200 times the tangent of 37 is pretty close to 900, and that approximates to about 30 meters per second. So we got to be pretty accurate at about 30 meters per second in order to navigate this circle on the banked curve without any friction. Now, to wrap this up, let's look at two situations in which you're going to have friction, but we're going to look at the minimum speed needed to make the frictional turn and the maximum speed. What's the fastest you can go and have friction aid in keeping you in the circle? Now, for the case of the minimum speed, I want you to think of it like this. You have your road, okay? This is your curved road right here, okay? And here's your car at various points on the road. That would be the normal path taken if it were going at some constant speed like we were before, and it's a perfect circle. The problem is minimum speed. What happens is the pathway is going to drift a little inward to the circle here. Now, to prevent this drift, friction is going to go up the plane to prevent this. So we've got the mass of the car going down, or mg rather, going down. You've got the normal force going up. You're going to have components of the normal force, which is n cosine going straight up and n sine pointing towards the center of the circle. But you'll also have friction going straight up, going up the incline. Friction going up the incline, you're looking at a top view here. Friction going up the incline prevents this drift inward towards the circle, which is kind of what it wants to do if you're going slow through the curve. Now, again, we want all of our vectors relative to, going to the right because we need centripetal acceleration, which points to the right. So friction needs components as well, just like normal force did. So friction is going over and up. This is the same as the angle of incline, similar triangles there, which means this is going to be friction cosine of the angle, and this is going to be friction times the sine of the angle. Do keep in mind, friction is just going to be mu times normal force times the cosine, and this is going to be mu times normal force times the sine. Okay, we're going to use that. Okay, so in this first case, in the y direction, again, your forces are balanced. Forces up equal forces down. We're balanced in the y direction. Now going up, how many forces are up? We have F sine and N cosine balance mg. So N cosine of theta plus mu N sine, that's friction sine, balance or equal the weight. So I'm going to call that equation number 1. Okay. And in the x direction, you're accelerating centripetally. So causing force minus opposing force equals mv squared over r. There is no outward force from the circle. Oh, no, I'm sorry. Yes, there is. I didn't look carefully on that one. So into the circle, we have n sine theta. Out of the circle, we have this one here, f cosine theta. So minus mu n cosine theta equals our mv squared over r. I'm going to call this equation 2. I'm going to divide equation 2 by equation 1. Before I proceed, I am going to factor out a common normal force from each side of the equation. And so normal force is going to end up being sine theta on the top minus mu cosine theta. And then over, right, and that's equal to mv squared over r. And then we factor out a normal force on the bottom, and we're left with cosine of theta plus mu sine of theta equals mg. And look at all the stuff that cancels now. Normal force cancels, mass also cancels. And so we are left with sine of theta minus mu cosine of theta over cosine of theta plus mu sine of theta. And all of that's equal to v squared over rg. So to solve for v max, or actually this would be v min, we're talking about the minimum speed, we have to multiply by rg and then square root. So v min is going to be the square root of rg times that big old mess there, sine of theta minus mu cosine all over cosine of the angle plus mu sine. All right, let's plug into that. The radius of curvature was, what was it? 120. The radius of curvature is 120 times 10. And then we're going to be going times the sine of 37 minus 0.5 cosine of 37 over cosine of 37 plus 0.5 sine of 37. Okay, so V min would be equal to 1200. And then what do we have on top here? Well, all of that on top, sine of 37 minus 0.5 cosine of 37 is 0.2. And then on bottom, cosine of 37 plus half of sine of 37 is about 1. So that would be, let's see, 0.2 times 12 would be 240, and the square root of 240, so the square root of 225 is 15. So the square root of 240 is about 15.5 meters per second. That would be the minimum speed needed to allow friction to prevent the car from drifting towards the center. Let's go ahead and balance this work with the case for maximum speed. Now, if I redo this picture here, for maximum speed, it's exactly the opposite. See, if you're going too fast, then what do you want to do? Your car wants to drift out of the circle, right? That means friction has to go down the plane to prevent this drift up into the wall, which is up the hill. Okay, so what is the force going to look like? We're going to have mg still going down. We're going to have normal force still going out of the plane. We have normal force cosine of the angle going up. We still have normal force sine in the direction of centripetal acceleration, which is towards the center. But this time you have friction going down the plane. Friction is mu n. So you're going to go down and over. So this is going to be mu n sine of theta, because that's the opposite side. And this side down here would be mu n cosine of theta. All right, let's look at our forces. So I guess we can start anywhere. X direction, which would be the centripetal direction. We have causing force minus opposing force equals mv squared over r. You actually have two causing forces this time. You have n sine and you have friction cosine. You have no opposing forces because nothing is going out of the circle. So n cosine plus friction cosine, n sine, the top component, n sine, plus friction cosine, which would be mu n cosine, equals mv squared over r. So I'll call that equation 1. And then in the y direction, where forces are balanced, we have one force going up n cosine, balancing two forces, mu n sine, and the weight. Now I'm going to take the mu n sine value right here and I'm going to subtract it over here. You'll see why in just a second. N cosine minus mu n sine equals mg, and I'll call that equation 2. I am going to take equation 1 and divide it by equation 2. So the reason I brought mu n sine over is so that when I factor out my common n, it's on the same side of the equation. Makes a big difference. So factor out your common n. And so normal force is equal to sine theta plus mu cosine theta. And that's equal to mv squared over r. And we're dividing all of that by, factor out the n, we're left with cosine of theta minus mu sine theta equals mg. Before we go any further, yes, the same things cancel. And yes, we end up with nearly the same result. So sine of theta plus mu cosine all over cosine of the angle minus mu sine equals v squared over rg. Let's pause and reflect on this for a minute. Minimum speed, we have this equation. Maximum speed, we have this equation. What's really the difference? Minimum speed, we have minus on the top, plus on the bottom. Maximum speed, the signs are reversed, aren't they? Let's solve for Vmax. Multiply by Rg square root. $120 times 10. Now on top, we have the sine of 37 plus a half of the cosine of 37. On bottom, we have cosine of 37 minus a half of the sine of 37. So Vmax would be 1200. Now sine on the top there, sine of 37 plus half of cosine 37, you might remember that was this value right here, and we got 1 on top. And then cosine of 37 minus half of sine 37, that was what we wrote up here. And that would be point. Oh, actually, no, it's not exactly the same. No. So cosine of 37 minus half of sine 37. Let's put that in our calculator. We actually have about 0.5 there. And when we divide by a half, you're really multiplying by 2. And so 2 times 1200 is 2400. Now, that's about almost 50. 2500 would be 50. 2400, we're looking at 49 and some change. So I'm just going to round it down to 49 meters per second. So that represents the maximum speed. So let's recap what we found out in this particular banked curve part of the lesson. When we have no friction, we need to go exactly 30 in order to navigate the curve. When we do have friction, we can go as low as 15. That's the lowest we can go to navigate the curve. And friction goes up the curve to keep us in the curve and prevent us from drifting downward into the circle. The fastest we can go around that circle and have friction keep us in the circle is about 49 meters per second, because the friction will now be going down the plane to prevent us from drifting up the plane. Again, remember to note any questions that you have about any of the examples you didn't quite understand.